Is it visible?
Yes, sir.
What about others?
Sir, I have told in WhatsApp group to
Hmm.
join them.
Is there any problem?
No, sir. One or two tell me that to forward the link to WhatsApp. So I am now forwarding the meeting link to WhatsApp, and then they will join.
Why? Because I have uploaded it in Google Classroom, and I think everyone has been joined already.
Yes, sir. I have joined from Google Classroom, but
Hmm.
some of them are using PC, so they don't have they don't have installed the Google Classroom in PC, or they don't want to open it in Chrome. So they told me.
So how can they? Okay, Srishti is coming. So how can they access these documents, the video links or the PPTs, lecture
I
notes?
think they access the documents from mobile, but when they are doing class, then they join with PC.
Okay.
Because in mobile, the shared content is very small, so the letters are not visible clearly in mobile.
Oh, okay. Okay, so let's start.
Okay, sir.
Mm. So last day I have discussed about the diffusion and implantation and some of the materials those are used in MEMS, but that material topic is not concluded. So that is the remaining. Here is the remaining portion. So the composite MEMS material. Uh, Today I'd like to discuss about some of this MEMS material and another portion which is related to some mechanical properties uh, of the materials. Okay, those are used in MEMS. Okay, because I need to recapitulate the certain portion of the mechanical which you have already read in, I think, in first year mechanicals. So strain, strays, these are. Okay, I just review it after certain slides. So now let us come into composite MEMS material. So composite materials are basically combinations of materials from different groups, which um, I mentioned four groups are metal, semiconductor, polymer, and ceramic. Now of these four groups, if you combine materials from different group to obtain the desired material characteristics, then it is known as a composite material. Okay, if you combine materials from these four groups, for four different group to obtain the desired material characteristics, then it is called a composite material. Okay, and a lot of research is going on composite material to achieve various specific properties. If you combine the metal with ceramic, if you can combine polymer ceramic and metal also. Sometimes semiconductor materials are also used to have some composite thing which has got unique properties or unique application. So these materials are used as passive materials in microsensors or in any MEMS based devices. Okay. Also, smart materials basically when used as an active material in MEMS that can be used is in MEMS based devices or MEMS based sensors, okay, microsensors. So here smart means it will have certain unique properties Yes, everyone mute yourself. If you have any question, I will ask you, then you can uh, ask me the. Okay. So what does it mean? Smart means it will have certain unique properties we does not have in case of we in metal, semiconductor, ceramic and polymer. So that is why it is known as smart. So it has specific property you can create by combining materials in different proportion. Okay, so electro active polymers examples mean is polypyrrole. Okay, polypyrrole that is used as chemoresistive sensors in an electronic nose. Okay. So if you go through electronic nose in website, if you search it, so what is electronic nose or how this electronic nose can be formed, it is artificial nose. So in that case, this chemoresistive sensor, chemoresistive material polypyrrole can be used. So electronic nose on device which can sense different gases, different sting. That is why known as electronic nose. And there the polypyrrole material is one that is used as electroactive polymer. So that is used in those cases. So now these are the different classes of materials used in case of MEMS. So I will discuss little bit of uh, this. So already I have discussed about the, I think, silicon material. Some of the portions I have covered. So, silicon substrate. So silicon is the single crystal silicon. Okay, there is a single crystal silicon. So in that respect, I will discuss on the some material properties and some definitions. So here three kinds of materials: crystalline, polycrystalline and amorphous. These three kinds of materials are used in case of crystal. So there is a difference between the crystal and polycrystal and amorphous material. Okay, and there is so certain differences are there. Now you should not confuse yourself between polycrystalline and amorphous. So there is a difference. Okay, so crystalline is known because uh, it will have long range regular order and a periodic arrangement of atoms in a crystal. Okay, and that periodic arrangement of atom, these are known as the lattice, basically lattice, and all the atoms in a crystal are located in the lattice points, and the distance between the lattice point is known as the lattice constant. Okay, so this periodic nature in a long range will maintain. Yeah, that is single crystal silicon. But if you look into the polycrystalline here, this third figure, polycrystalline or microcrystal, sometimes it is called microcrystal also. You can say in a small region it is crystalline, but throughout the whole bulk of the material it is not crystalline. It is polycrystalline. Okay, it is not in regular form. Okay, so this portion is in regular form but not whole device means whole material. Okay, it is in disorder manner. Hmm. So regular order is in within this range or this range or this range here, but not in full region. So on the other hand, this the amorphous, there is no regularity between the crystal lattice structure. It is highly irregular. Okay, irregular, and the crystal are, or atoms inside the crystal are oriented or all placed in different direction, here and there, different direction. So in the uh, haphazard direction, it is known as amorphous material. One example is, if you evaporate certain metal film on a single crystal silicon substrate, then this film is amorphous film. For example, if you implant silicon by certain ion in ion implanter, the region where the implanted spaces will locate will uh, those regions initially it will be highly amorphous. Okay, after that we have to do centering or annealing, so that again you will get back the regular silicon single crystal structure. So those are the amorphous examples. Okay, polycrystalline is also an important material which is used in sacrificial layer, sometime used as sacrificial layer, sometimes structural layer in case of a MEMS, so that it is achieved by CVD technique, chemical vapor deposition technique, or sometimes by ion beam deposition technique. Okay, we can get the polycrystalline material. Okay. Now in these crystals, a set of integer known as HKL, those are also called Miller indices, is used to identify a set of planes or direction. These are the planes. This is one plane, this is another plane, and this is another plane, and these are the direction. Okay, so this is X, Y, Z. Assume. Okay, so it is so so when you are using that silicon, sometime you will see that it's a 100 silicon, or 111 silicon, or 010 or 001 silicon. So different crystal planes are also cited along with the single crystal uh, silicon, and those planes, how to define those planes? Those planes are defined by with the help of these integers, which are Miller indices. Okay, so for example, silicon, basic silicon, it's a cubic structure like this type of cubic structure. You can see that the XYZ, this three axis, and this is a cubic crystal structure. Now if a plane which is perpendicular, perpendicular, say this is X, this is Y, and this is Z. Okay, so a plane on the on this axis here is it, and this axis. So the plane particularly, it is known as, according to this axis, it is known as 100 plane. Okay, and in this direction, if you go in this direction, the plane is called like in this case, second figure. So this plane, this plane, it is called 110. It is called 110. This cutting. Okay, because we have this axis, and this axis. So according to this origin, if you take this direction as 1, and if you cut through this portion, this plane, so this plane will be used as 110 plane. And in this model here, this axis is 1, this axis is 1, this axis is 1, and according to this origin, if the direction is in this position, and if you cut through this position, this triangle shape, then it is known as 111 plane. Okay, so there are the different structures are available, according to which we can select it, which material, like which type of silicon material can be used, whether it is 100 silicon, or 110 silicon, or 111 silicon. Okay, so So if you cut the plane in different parallel to certain axes, so in that particular plane, the number density of the silicon atom will not be the same in all the directions. Okay. Now, one point is also important. How do you identify crystal is 111 or 100 or 001, or how do you identify this? So one technique is by X-ray technique, but always in the laboratory you will not have the X-ray technique. So there are certain nomenclature which is followed uh, everywhere by the manufacturer of silicon wafers. So accordingly, by seeing a silicon wafer, like this is the silicon wafer, these are silicon wafer, okay, round in shape, but certain flats are available. Okay, so accordingly, by seeing a silicon wafer, we can identify whether silicon crystal slice is 111 directions, or it has 100 direction or 110 direction. So these are the figures. You can see this is cut here. This is known as primary flat. Okay, it is cut here. First, the silicon wafer, it is in round form, then it is cut and it called, this is primary flat. Okay, this is a circular thing. This is the primary flat, and here this is the another cut which is called the secondary flat. Okay, and the angle between this primary flat and secondary flat is 45 degree. Now if a primary flat and secondary flat is made like this, then this silicon slice is 111 N type silicon. Similarly, if only the primary flat is available, then it is known as 111 P type silicon wafer. So those flats are made from the manufacturer, so their company will make those flats. So accordingly, by seeing a silicon wafer, you will identify these P type 111, and this is N type 111. So in other hand, if there is a flat here, this one, primary flat, you can see it's longer than the secondary flat. This is the secondary flat. Okay, so there are two flats. If we, but it is in 180-degree direction. It is opposite to each other, 180-degree direction, and it is called as 100 N type silicon wafer. Okay. Similarly, if there is a primary flat, if there is 90-degree orientation is there, primary flat and secondary flat, then it is known as 100 P type silicon wafer. So in case of the MEMS devices, or even in VLSI devices, so normal wafers we use nowadays is 100 silicon wafer mainly. Okay, there are certain advantages of that. Main advantage is that the 100 silicon can be cut into small pieces regularly in regular way. Okay, it is very easy, because whatever devices you made either in a VLSI chip or MEMS, at the end you have to separate the chip, you have to break the chip. So 100 wafer can be broken in a regular fashion, and you can have the small pieces of die. But in 111 you cannot break in regularly. You have to use some diamond saw, and even then some of the pieces will break in different angles. Okay, it is hard to cut. So some of the pieces you can lose in this way. So that is why 100 is a popular oriented crystal that is used, but for certain specific application in MEMS we also use 110 010, this type of, okay, or 111 oriented silicon wafers. Okay, so this is the crystal structure of the uh, silicon, um, single crystal silicon, and that is, you can see bond, and it belongs to more general zinc blade structure. So here every is this is one. So this is silicon, this is silicon, this is silicon, so this is silicon, so all these are uh, basic, this is a atom. So and between this one phase silicon is there. Okay, this is a basic structure of crystalline silicon. Okay, so now we'll discuss something on what I have told you earlier, the mechanical properties, okay, on materials, because MEMS, as you know, this is a micro electro mechanical system. Okay, so mechanical properties and its definition you should know. So although some definitions are known to you, again I will review those definition. I will remind those definitions, because when you are going to design, it's very important to know or to aware those definitions accurate. Now some is axial stress and strain, and some are known as shear stress and strain. So what is the different so definitions are available, and what is the difference between this axial stress and strain and other shear stress, shear strain? So in this slide, axial stress and strain is described. For example, here this is a bar, rectangular bar. Now if you apply force axially or normal to the surface, because the force is applied normal to this surface, and along the axis the force is applied. Okay, so now if you apply the force in axial direction, is length has been increased, length has been increased in this direction. Okay, in these two directions, but we assume that diameter is not changed, the diameter is not changed. In ideal condition, let us assume the diameter is not changed. Okay, ideal condition, but length is only changed, length is only changed. Now this is known as the axial strain. Axial, okay, if you apply stress only on perpendicular surface along the axis, the diameter is not changing but length is changed. um, then it is known as axial stress, and that means the force per unit area. Okay, which is uh, here given, it is Newton per meter square. Okay, so this is and next is the normal strain, so which is epsilon del L by L. Now del L, what is del L? And so if it is L, the length is L. Okay, and the change of length is del L. Okay, so L plus del L, that is the change. So here normal strain epsilon equals to del L, the change of length divided by the actual length, which is called normal strain. So how much um, in the how much increase in the length direction, that is uh, del L by L, is known as normal strain, and Young modulus or elastic modulus, which is E, defined by stress by strain. Okay, so sigma by epsilon. Okay, that is Young modulus or elastic modulus, which is an important mechanical property which will be used for designing any micro mechanical structure using silicon. Okay, and this is the curve of stress versus strain. If you increase stress, it will just follow a straight line path, and strain will means elongation will be there in certain perpendicular direction. So this is a stress strain curve, and so long it is linear, it is used. And as it becomes non-linearity, so then it some other deformation takes place basically in this. So long it is linear, if you reduce the stress, strain also reduced. So that is, if you expect there should not be any hysteresis. Okay, so stress strain curve, this the linear region is used for making micro mechanical devices or sensors. Okay, so now Young modulus is or elastic modulus, whatever, both are same, is basically stress by strain. Okay, so here one so there are two types of stress, tensile stress and compressive stress. Okay, so tensile stress in that is positive in nature, other is a compressive stress which is negative in nature. Now compressive stress, we call it negative stress, and tensile stress we call it positive stress. And higher the E, less the material deforms, because E value is more, the deformation will be less. Okay, that E is anisotropic in nature, and uh, it's very important and a function of crystal direction. That E means Young modulus or elastic modulus, which is anisotropic in nature. Okay, so the different for different in different crystal oriented direction, crystal plane value is different, and it is not the same, and that property may be used to make certain senses to for certain applications. So other is the shear stress and shear strain, which will be discussed in the later in this slide. Okay, shear stress and shear strain. So here also I have taken an example, like this is a block, and in that block force is applied parallel to this surface. This is surface which is fixed. This parallel force has been uh, given. So in other case we have shown axial force is applied perpendicular to this surface. Now this is the lower part which is fixed, upper part of this body we have applied force in this direction parallel to this surface. Okay, so what happened, the top plane is deformed and bottom is fixed. Initially it was in this shape initially. So later on, if you apply force at the top of this surface, it bends in this direction, this dotted line, this one, the dotted line is a new position. So what is the change in delta x? What is the change in delta x? Delta x is change in this direction in which we have applied force. Okay, displacement. So here is, this is the displacement. So this delta x divided by length L, the one side of this particular object. Okay, so this delta x by L is called the shear strain, that is by gamma. And shear stress is again that is force per unit area, okay, which is in Newton per meter square or Pascal in SI unit. Okay, so it is represented by tau. So shear stress is tau, which is Newton per meter square. Okay. Now the modulus of shear, it's called shear modulus, shear modulus of elasticity, which is represented by G. That is by that is equal to tau divided by gamma. Okay, that means stress by strain again. So here we will have shear stress and strain, shear modulus or shear modulus of elasticity. So that is known by G. G is again stress by strain, which is tau divided by gamma. Okay, in case of shear. So the higher the E, less the material deform, like the axial strain. Okay. Another important point is for isotopic material, E equal to G. What is E? E is the elastic stress and G is shear strain. Elastic modulus or the shear modulus. Okay. So elastic modulus and shear modulus will be equal for isotropic material. Okay. Different isotopic materials are there, like silicon dioxide, silicon nitride, silicon dioxide, diamond is there. So these are the isotopic material. Okay. Okay. So that's all for today, because we have one seminar of SPIE. All of you must join that seminar. Yeah. So that's all for today. If you have any queries, any doubt,
No, sir.
okay. So today's attendance: Supratik, Sishti, Sanaz Alam. So where is Atul? He was joined previously. Okay. Okay. So thank you very much.
Thank you,
So,
sir.
okay.
Okay,
So
sir.
see you
Thank
on
you.
Friday. Okay. Okay.
Okay. Thank you, sir.